Hello, AP Physics students. These are for my tennis players that were missing. I didn't want you to miss out too much. Just a little bit of overview what we have done in class. We started understanding, we've been learning about position time graphs, and we're trying to transition into a velocity time graph. And so we had a position time graph, and it's constant speed with a positive slope if we assume 1 to 1. We've got a constant velocity in a velocity time graph, so a positive 1. And then a negative slope, right? A negative 1, and it's constant. If this is 0, 0, it would be a constant in that horizontal. This is where fourth period left off. Pretty similar as far as how to go about it now. This will be the interesting part because I forgot my whiteboard is in the sailing closet. So let's see if we can do some stuff, some magic. I can actually draw. All right, there we go. So again, the last one started at 0, 0 as far as position time, right? But ultimately, the slope is still, let's see if I can get a color here, and maybe I'll go a little narrower. The slope is still starting at negative 1 and is horizontal. Now I've got something that's piecewise. We call it piecewise because it's honestly not realistic. For something to turn around, right, it's got to slow down and then it's got to speed up again. But starting at 0, we go in the negative, so we have a negative constant velocity of negative 1, and then I'll just put a little circle, and then it turns into positive, like that. So that's what the velocity time graph would be. You show it constant in the position time with the constant slope, but in velocity time, it's horizontal. Constant velocity shown there. If it had a slope, which we'll talk about in just a bit, what do we do with that? Okay, hopefully that worked. Now, what happens if I start with velocity time? First of all, this little x with a subscript 0 means the position, x, at time 0. So on this graph, right, it'll start at 0, 0. So I'm going to see if I can get this where I can draw on it again. Get that bit nice and big. Sorry, again, no whiteboard. But I start at 0, 0, right? And then what is my slope? So if this is the slope, what is this constant velocity? If again we assume units of individual 1 unit, 2 units, and the positive, this is that 2 meters per second, right? A little long. So I'm going to go on position time, start at 0, 0, up to over 2, up to over 2, and up to over 2. And we kind of go off the graph, but we'll have a nice straight line if I weren't using a mouse. Blah. Okay. The other over here, so we've got a negative velocity, and it says I'm starting at time 0 at 3, 1, 2, 3. And then it's a negative 1 slope, down 1 over 1, or down 2 over 2, right? However you want to do it. And a nice straight line like that. So you can go from a velocity time graph back to a position time graph. Now something we had talked about a little bit in class is there's other information you can get from a velocity time graph because velocity equals your change in position or your displacement over your change in time, right? That's our equation we got in class. Well, what if I want delta x? I did a little algebra move, and delta x equals what? Right? Coolest thing is the algebra works and the physics works too. My velocity times delta t. Okay? My velocity times delta t, like I'm going 60 miles an hour for 2 hours, right? So what do I get? 120 miles, right? I'm driving 30 meters per second for 10 seconds. 30 times 10 gives me 300 meters. So a velocity times that time interval gives me my distance. So if we go to a velocity time graph, my velocity of 2 over 1 second, right? 1 second gives me this little rectangle. I like to use the rectangle, right? A delta x, and you'll see why I like the rectangle, of 2 meters, right? 2 meters per second for 1 second. And guess what? Delta x from here to here, delta x right? Oops, equals 2. This is really hard. I wish I had a Chromebook. Oh well. So what if I had gone another 3 seconds, right? What would my delta x be? Well, that would be 2 meters per second times 3 seconds for a total of, right, this space, 2 times 3 is 1, 2, 3, 4, 5, 6, so delta 6. So in the next 3 seconds, 1, 2, 3, I go up 6, 1, 2, 3, 4, 5, 6, which would be right around here. So I've got this delta x of 6. There's a correlation with the area between your data and 0 that correlates with your displacement. So I can be on a velocity time graph and find displacement. Okay, so let's go to the next slide. I know this is not going super fast. Let's see if I can do this here. So an interesting thing we did in class is what could we find in a position time graph? Well, we can find our position at any certain time. That's easy. But we could also find out if we were moving forward, right, and at what speed, or backwards. So we could determine our direction and we could determine our speed based on our position time graph. What can we learn from a velocity time graph? We could learn our starting position. They don't have to tell us that. We could find out that we're going forwards or backwards at a certain rate. For instance, this is a -1, so I'm going backwards at a 1 meter per second. And then what we were saying earlier is we were able to find out displacement by finding out, not distance, but displacement by looking at an area between the data and 0. So -1 times 5, my displacement would be a -5. So I'd be going backwards 5 units. It's kind of nice. The other thing people are like, well, what's the slope mean? Because before the slope meant something. So let me see if I can write some of that down. It's weird because this slope, right, it's horizontal, 0. What does that mean? That means my change in velocity, right, over my change in time equals 0, right? So what is 0? What is a change in velocity over time? And I usually pull up, if I'm driving and I'm at the stop sign, right, I'm at 0 velocity. Well, my velocity has to change. What do we call that when we step on the gas? We call that acceleration. So acceleration, we introduced that concept, acceleration equals change in velocity over change in time. So what are those units? You're changing in meters per second, that's your change in velocity, meters per second every second. Meters per second every second, which essentially is meters per second squared. So I'll keep going. I know I'm getting close on time. What if the graph looks like this, where your velocity is changing, right? It is changing. So what's it doing? I'm at a +3, a +2, +1, +0. So I'm slowing down. Well, I also have this negative slope, which would correlate with a negative acceleration. But watch out, that doesn't mean you're only slowing down. What do we do once we get here to 0? Right? Now I'm at a -1. What's -1? Right? What's -1 meters per second mean? Well, it means I've been going forward, and now I'm going backwards, and then -2 meters per second, -3. So reading through that, right, is pretty nice, okay? But you got to be careful. A negative slope doesn't always mean you're slowing down, but it is correlating with acceleration. So negative and acceleration don't always mean slowing down, is what I want to say. Okay. So then we did a little exercise here, right? If before we were able to do the velocity times the time to get the displacement, what would we do when it's changing? Okay. So I'm going to just say, right, I'm going to highlight an area. How much distance am I changing over 2 seconds, right? And the algebraic way is, well, you are at a 3 meters per second here, right? And then you're at a 2 or a 1 meter per second here. But it's changed at a constant rate. So what we're able to do is what's the average velocity between 3 and 1? And that's V average, V average equals 2 meters per second. Okay? So I take the average velocity multiplied by my time, right? And I get, what, 4 meters. Okay? Now the cool thing is, I think this is cool. Check out the blocks. Okay, I'm going to change this a little bit. Check out the blocks. How many blocks do I have? I've got 1 block, 2 blocks, 3 blocks, and then 2 half blocks for a total of 4 meters. The coolest thing about this, I'm giving you another way to calculate displacement. Displacement can be calculated, just like we did before, by finding the area, right, between the data and your axes, your time axes. So if I went 3 seconds backwards, I'd have 1, 2, 3, 4, right? And then 2 halves, all right? Oh, no, sorry, my bad. 1, 2, 3, and then 1.5 for a total distance of 4.5. Okay? So we'll do that in our homework. I'm getting right at 11 minutes, so let me try to close this up. You've received a PDF handout of the homework. Okay? There are probably about 10 questions associated with it. They're going to ask you about displacement. Okay? Oops, I didn't want that. Let's see if I can do that. That's going to be bad. I guess I can write on that. Oh well, I guess I can write on those things. I guess I should just do that. Let's get that up. No, maybe not. So when I write on these things, right, if I want my displacement or distance, I can get that area, right? So that's 6, right, and 5 seconds. 6 meters per second. For 5 seconds, I've gone 30 meters. Okay? Now, what do you do for this one right here? Okay, what do I do for that one right there? Well, I can find the average velocity between 12 and 6, which is 9, times 5 for 45 meters. Okay? Or I can see this space as 30 and this space as 15 to get me 45. So you're going to be asked about its velocities at certain times. You're going to be asked about displacement. You're going to be asked for distance. You're going to ask, are you heading south? Or are you heading north? So you're going to read this graph, right, and try to answer those questions. I hope that helps. We'll see. Let's see if I can get out of this.